Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like parallel scalability laws, metrics, factors, efficiency and load imbalance. Let's get started. Slide 1. Parallel Scalability Introduction. Hey everyone, today, we are going to discuss parallel scalability, which is an important aspect of high-performance computing. Parallel scalability refers to how efficiently a parallel system improves its performance when we add more processors to it. In simple words, if we increase the number of processors in a system, we expect our program or computation to run faster. But how well this actually happens is what we call scalability. When a system is said to have good scalability, it means adding more processors directly reduces computation time or allows us to handle larger workloads effectively. For example, if you are running a simulation on 2 processors and it takes 1 hour, ideally, running it on 8 processors should take only 15 minutes. But this doesn't always happen due to various factors, which we will discuss. Scalability is crucial in real-world applications like climate modeling, AI training, and data analysis, where computation needs are very high. The aim of today's session is to understand what affects scalability, how we measure it, and how we can improve it to make parallel systems more effective. Slide 2. Parallel Scalability Laws, Amdahl's and Gustafson's. Now, let's talk about 2 very important laws that define the limits and possibilities of scalability: Amdahl's law and Gustafson's law. Amdahl's law tells us about the maximum possible speedup when we parallelize a program. But it also reminds us that if a part of the program cannot be parallelized, then adding more processors will not help much. For example, imagine a program where 30% of the code is serial, meaning it cannot be divided among processes. Even if you add 100 processes, that 30% will take its own time. So speedup has a limit when serial portions are present. The formula for Amdahl's law is speedup equals 1 serial fraction plus parallel fraction number of processes. On the other hand, Gustafson's law takes a different perspective. It says that if we increase the problem size as we add more processes, we can still achieve good speedup. This is very practical because in many real-world cases, as we get more processes, we also increase the workload, like analyzing larger datasets. The formula for Gustafson's law is speedup equals serial fraction plus parallel fraction times number of processes. So while Amdahl's law focuses on limits, Gustafson's law shows us opportunities to scale up. Both are essential to understand how much speedup we can expect and under what conditions. Slide 3. Parallel Scalability Metrics. To measure how scalable a parallel system is, we use various metrics, which help us evaluate and improve system performance. 1. Speedup is the first metric. It tells us how many times faster the parallel system works compared to a single processor. For example, if a task takes 10 seconds on one processor but only 2 seconds on 4 processes, then the speedup is 5x. 2. Efficiency measures how well processors are utilized. It's calculated by dividing speedup by the number of processors. If we have a speedup of 5 using 10 processors, the efficiency is 0.5 or 50%. 3. Scalability factor is a broader term, showing how well the system performs when we increase both processors and workload. 4. Strong scaling measures performance when we keep problem size fixed but add more processors. 5. Weak scaling looks at what happens when we increase workload proportionally to processes, useful when data grows. 6. Parallel overhead refers to the extra time wasted due to coordination and communication between processes, thus reduces speedup. 7. Load imbalance happens when some processes have more work than others, causing inefficiency. 8. Latency is the communication delay between processes. High latency affects performance. 9. Throughput is the total number of tasks completed in a given time, showing system capacity. By analyzing these metrics, we can understand whether our parallel system is working efficiently or needs improvement. Slide 4. Factors affecting parallel scalability. Even if we add more processors, many practical factors limit scalability. Let's look at them. 1. Communication overhead. Processors need to exchange data, and this communication takes time, especially when data is large. 2. Synchronization delay. Sometimes, processors must wait for each other to reach a certain stage, thus, waiting time slows everything. 3. Load imbalance. If tasks are not divided equally, some processes finish early and sit idle, reducing overall efficiency. 4. Memory bottlenecks. All processes need access to memory. If memory cannot supply data fast enough, processes wait, and performance drops. 5. Algorithm design. Not all algorithms are good for parallel execution. If the algorithm cannot divide work properly, performance suffers. 6. Hardware limitations. Network speed, processor types, and architecture can limit scalability. 7. Software overhead. Managing tasks and communication also takes time and can reduce net performance. 8. Problem size. If the problem is too small, adding more processors won't help because there's not enough work to distribute. 9. Data dependencies. Some tasks can't start until other tasks finish, causing delays. Understanding these factors helps us optimize our system and choose better algorithms for parallel computing. Slide 5. Efficiency and load imbalance in parallel systems. Let's now focus on efficiency and load imbalance, two key issues in parallel systems. Efficiency measures how well we are utilizing the processors. If all processors are busy doing useful work without much waiting, we have high efficiency. High efficiency means faster task completion, better use of hardware, and lower energy costs. High efficiency happens when tasks are well divided, and communication delays are minimized. Load imbalance, on the other hand, is a major problem that occurs when some processes get more work than others. If some processes finish early while others are still working, those idle processes waste time. Load imbalance happens due to uneven task division, variable task complexity, and sometimes hardware differences. For example, if in a matrix multiplication task, one processor gets a much larger chunk of data than others, it will take longer, and other processors will wait, causing inefficiency. Hence, balancing the workload and managing dependencies are essential to avoid load imbalance and improve overall system performance. Slide 6. Advantages and disadvantages of parallel scalability. Let's finally discuss the advantages and disadvantages of parallel scalability. Advantages. 1. Faster task completion when we use multiple processors. 2. Better use of computing resources. Processes are utilized efficiently. 3. Enables solving very large and complex problems, like scientific simulations. 4. Improves system throughput, allowing more tasks to be completed quickly. 5. Systems can scale up to thousands of processes, handling big workloads. 6. Flexible, we can adjust the number of processes as per need. 7. Often cost-effective, as tasks finish sooner, reducing power and time costs. 8. Provides fault tolerance, because if one processor fails, others can continue. Disadvantages. 1. After a point, adding more processes gives little speed up, known as diminishing returns. 2. Communication overhead becomes large as more processes are added. 3. Writing efficient parallel algorithms is complex and challenging. 4. Load imbalance can waste processor time. 5. High hardware and maintenance cost for large clusters. 6. Synchronization between processors adds complexity. 7. Not every problem can be parallelized. 8. Managing parallel software increases complexity. 9. Dependent on network speed, especially in distributed systems. So, while parallel scalability is powerful, we need to design systems carefully to gain maximum benefits.